Hello, thanks everyone for coming to a new seminar. We're really happy to have Alvaro Lorca.
Okay, thank you, DIIIO. Thank you. Okay, so my English is probably a bit rusty because I haven't used it too much. So I'm glad that the talk is in English. That way I practice a little bit. Okay, so this talk should really be called a bit about the stuff I do, or something like that, because I'm going to talk a lot about different things, and not only about planning in energy, but also about better. I think that's better. But also about operational problems in energy. Okay, so I will talk about things I've been doing since probably 7 years or something like that. Some of the stuff I did in my PhD and some of the stuff I'm doing right now. Okay, so as DIIIO said, I'm from Universidad Católica. I'm part of the Department of Electrical Engineering and also the Department of Industrial Engineering. Okay, for the last 3 years. So this is a motivating question for me, and a motivating question that we should look into as a society all the time. Okay, so we've been struck by a particularly crazy couple of last years. Okay, and climate change is the main story. Okay, and for example, in Chile, there has never been, as long as we have records, there has never been 10 years with this little water, okay, a drought that we're experiencing. So was 2018 the worst year ever? No. 98 was worse in terms of water. But if you look at the 10 years, okay, this is the worst 10 years ever. Okay, so from 2020 to 2020 or something like this. Okay, so how will the energy sector look like, say, 30 years from now? And we can ask this question maybe 1 year from now, 5 years from now, and 30 years from now, and we need different tools for analyzing these kind of things. Okay, so this is my main motivating question. And then also, the question is, how are we going to run and operate that future energy system? So I'll try to draw onto different aspects into these questions. Okay, so a little bit more about me. I did my PhD at Georgia Tech in operations research. I worked on optimization in energy mostly. Before that, I did my undergrad and master's at Universidad Católica as well. Okay, and a lot of the stuff I'll talk about, I'm doing with my colleagues Daniel Olivares and Matias Negrete. We have a laboratory on energy. Okay, and energy from perspective of optimization, control, and markets. Okay, so there's a little bit of the stuff we do: demand response, loads of stochastic batteries, electricity market design, the concept of smart grid, algorithms, the concept of energy services, and so on. Okay. Okay, so I'll give a brief introduction into some of the questions I'd like to speak of today. Okay, then I'll talk a brief overview of robust optimizations. There's the 107 slides, but I'll probably use like 20, so don't worry. Okay, you won't be here until 3 p.m. Okay, we would need, so I'll probably talk until 12:20 or something. Okay, then a little bit of robust optimization in power system operations, energy planning, and if we have time, I'll just touch onto some other of the things, some other of the stuff I'm doing on optimization and energy-related aspects. Okay, so this is like a typical picture. Okay, when you didn't have this solar curve, this is 24 hours of operation in California. When you didn't have this solar power generation curve or this wind generation curve, I'm not going to say it was easy to handle power systems, but it was a lot more certain to handle power systems. Okay, so main difficult thing was probably generator contingency. Some generator telling you in 10 minutes I'll be out of the system because of some problem, or right now I'll disconnect because of some problem. Right now we had Argentina having a blackout last year because of some issues in some transmission lines. And that's really hard today as well. But what's making things really harder, a lot harder, is solar power and wind power. Okay, solar, it's not that variable. Okay, if you have some huge clouds, you might get some strange spikes here, spikes down. But wind is very variable. Okay, if you start increasing this signal, it will be very, very, very variable. So you're adding a lot more variability into the system. How do we handle this? And how do we change our operational and planning means to have reliable and sustainable energy systems? That's the question. Okay, so I'll be talking about optimization under uncertainty. First of all, you cannot rely only on forecasts. Okay, you need to understand how uncertainty somehow merges with your decisions. Okay, and we need efficient computational methods to handle high-dimensional uncertainty. So that's some of the challenges, and here are some of the critical points. Okay, so I'll just keep to this part. So what is robust optimization? For those of you that don't know it, okay, I know most of you might know what this is, but we'll brief very quickly into this. So what is a typical optimization problem? Okay, I have some function that I want to minimize, some constraints. And now the question becomes, what if I have some random parameters, some d vector? So this d vector will affect both my constraints and my objective. Okay, so we have here Bental and Mirovsky almost 20 years ago, telling us in this seminal paper that small errors in data values can make optimal solutions, optimal assuming that you knew some forecast, highly infeasible or very far from the feasible space if this D ended up being something different than what I expected. So how do we find solutions that are immunized in a way to these different possible Ds? That's the main question that robust optimization asks. Okay, so we have a very simple example here. Two cities, one transmission line, generator A, generator B, demand A, demand B. This generator is cheap, this generator is expensive. I want to supply most of this demand using generator A, but this line has some congestion. Okay? So this is a very simplified version of the model. You know, you minimize 10 PA plus 20 PB, some constraints over both generators, and some constraint over this transmission line. Okay? Let's say that you want to have at least as much demand, as much power generated as demand there is. So if we have 100 megawatts of demand here, 100 megawatts of demand here, the optimal solution is producing 130 here and 70 here. Okay? And it makes sense because you're producing as much as you can here, given that you satisfy the transmission line constraint, okay, which is this dynamics. But what if I tell you this dA and dB are really in this interval, and that's all you know? dA will be between 80 and 120 megawatts, dB between 80 and 120 megawatts. What would be a good solution now? So if I give you this solution, right, this solution, this is quickly infeasible if dB becomes 101, for example, or if dA becomes 101. This becomes infeasible, okay? So for example, just as an example, this other solution, generating 120 here and 120 here, is what we call a robust solution. Namely, this will be a feasible solution for any dA in this interval and dB in this interval. Okay, you can check all the different alternatives, and you see that this solution is feasible under all those circumstances, whereas this original solution is quickly, if you vary these numbers a little bit from 100, you deviate them from 100, then this immediately becomes infeasible. Whereas this is more stable in a way. So the question is, first of all, let's go back to this huge system. The power system is a really complicated machine. Okay, there's a lot of uncertainty, and I want to have some reliable control for it. So how can I find a reliable way to control this large power system? That's the main question. Okay, so sure. It's much more expensive, but you can check. For example, then you raise the question: what would be the cheapest solution that is reliable under any possible circumstance? And at least that one is. Then again, you can generate 140 at each place. Make sure you have enough energy. but then that's more expensive than this one. So yes, there's a trade-off between, reliability and economic effectiveness in a way. But then you can ask the question, and in a systematic way, ask the question: what is the best economic solution that satisfies certain reliability criteria? So that's the question. So the traditional, if you were to write a robust optimization problem in a very traditional way, or the simplest robust optimization problem in general, is this one. Okay? So I want to choose some decision such that some worst case cost is minimized under some D in this uncertainty set D. We will call this uncertainty set. And these constraints, I want them to be feasible for any D in D. Okay? And now this D set doesn't have to be a box like this one or two intervals. Okay? It becomes a huge question if I have, say, 1,000 dimensional uncertainty, 1,000 Ds, what would be a reasonable set? And probably a box or an interval for each DI, that's probably not a good idea. Okay? So there's a lot of reasons for doing robust optimization, and you find many different areas where it has been studied and employed. Okay? So I just want to touch on one key methodological idea. The question is exactly that one. How do we find the best solution such that this holds in a way? Okay? This transmission constraint I showed you before. So you can write this general robust constraint exactly as this. Okay? So in the worst case for this vector D, I want this to be less than or equal to some capacity of this line or whatever system it is. In this case, it becomes simple to analyze. But more generally, what you're studying is basically this expression here. Okay? If you have some linear relationship between some function of x and your uncertainty D, and your constraint is that you want this Cx transpose D to be less than or equal than some h, for all D in D, this is equivalent to this being less than or equal to h, and by duality, okay, this expression we have here, and we have some very general expression here written using cones, okay? By duality, we can write this in this way, and that means that our original constraint, that is here, we can write it as this equivalent system of equations using the dual cone of this cone here, okay? So in the linear case, you can just get rid of this k, just have greater or equal to here, but then you can also have S of CP over SCP here, okay? So this is the duality-based reformulation of robust optimization constraints, of robust constraints. Okay, and we can do a lot of different things. The question is, how do we build this set? We can actually also model correlations into these sets. I'll show you in a bit how. Another important aspect is when I have adaptive decisions. So what if I have to make this X decision now, and then I'll observe these Ds that appear over time, this D1, D2, and every time I observe these Ds, every time I make decision P1, I only know D1. I make decision P2, I know D1 and D2. I make decision PT, I know the story of the Ds up to T. So how do we model that? Well, the way to model that is we'll think of policies, okay, or functions. So now my decision space is a function. I want this PT to be a function of this information realized up to that point. Okay, so D brackets T. And then, for example, we could think of this problem over some time horizon, say 2 time steps, okay, and saying I want some reasonable function. Okay, so for example, a reasonable function could be this guy will always supply the demand of city A, and this guy will supply the demand of city B. That's this policy here. Okay? And then you can also think of some other things. Maybe this guy will supply half of the total demand, and this guy will supply half of the total demand. That would be another policy. Okay? And if that was linear policies, I could think of some non-linear expression as well. So it becomes a hard question. And I'll show you at least one case where that ends up appearing. Okay? So I don't want to go over this. It's too much information. I do want to show you this slide. Okay, so how do we add correlations? This is an uncertainty set we built for wind and solar power. Okay, so this is This is basically how much power do I have from renewable unit I, or wind or solar farm I, at time t. How do I build correlations into this expression? Why? Because if I know there's a lot of wind right now, it's highly expected that there will be a lot of wind in 10 minutes. Okay? But I don't know if that tells me anything about 8 hours from now. So that's a temporal correlation. And also a spatial correlation. If there's a lot of wind right here, there might be a lot of wind 5 kilometers from here, but maybe not 4,000 miles from here. Okay? So spatial correlations. So what we did is we thought of vector autoregressive processes. If you think if this V were a white noise process, or were some normal random variable IID vector, then this model for U would be a vector autoregressive process of order L. Okay? And then the spatial correlations are built into this matrix B, and the temporal correlations are built into this matrix A. But here, there is really no uncertainty at all. These are just some deterministic things. This is just a set. Okay? Now, the nice thing is we can build some confidence region for the white noise component. Okay? So this is just a confidence region. So this could be, if this is norm 2, this would be a ball. Okay, an L2 ball, which is a reasonable confidence region for a normal random vector. And then this structure here would build in temporal and spatial correlations. So we can capture that, and we show that this helps if you use robust optimization models for operating the power system, understanding a little bit of the temporal and spatial structure of wind and solar power. Okay? Okay, so another methodological concept. This is a classical model in robust optimization. Min, max, mean model. So the idea is this. You would have make some decision. Okay, so this is similar to this piece and this I showed you before, but just 2 stages. You make some decision, you have some cost associated to it, and then uncertainty or nature, if you will play some worst case move within some set. This is like this D set. Okay, and then after nature does this, I can make some additional decisions, okay, some second stage or adaptive decisions that depend on my first stage decisions and on what nature did. Okay, so famous application of this model, and there's been probably about more than 50 or maybe even more than 50 papers with this structure only for the unit commitment problem. So unit commitment is which generator should I turn on or off for the next 24 hours, okay? And people have worked on many different methods for solving this kind of problem, depending on the structure you have for this Y set and for the Xi set. Okay, that would be the main thing. So the key idea to formulate this, to solve this problem, you can reformulate it in this way with this additional variable that represents worst case second stage costs, and then you can write this problem in this semi-infinite way. Okay, again thinking of functions of psi, and then some ideas, at least to get approximate solutions, is to some sort of sampling over this space, or systematically finding bad scenarios. That would be the idea, and I don't have time for all the details. And then the main challenge would be anyways to solve this problem. Okay, if this y is linear, then you can use duality here and obtain a bilinear problem, a bilinear optimization problem that's still non-convex, but depending on the structure of this set or some approximations in the dual of this space, then you can find some reasonable approximating mixed integer optimization problem. Okay, and we've used those techniques. So a little bit of how we use this, or my work on how we've used these concepts in power system operations. Okay, so first we did some work on multi-stage robust unit commitment. I don't want to give all of the details, but just tell you that what we worked on was finding a reasonable policy for these dispatch decisions. So this X here represents on and off decisions of all generators. These are different generators in this network. Okay. Tell me what generators should be on and off. Give me a schedule for them. That's X. And the P is how much power each of these generators will produce depending on what renewables do. Okay, or in this case, just demand. Just these arrows represent demand. I don't know demand. Okay, and demand could incorporate wind and solar power as negative demand. Okay, so this will be net load. And we worked on some specially structured policies, some very simple Ps. Okay, so just what we ended up calling a simple affine policy, where what we did, let me just show you here. We found this way of controlling the system. This generator will have some nominal level, say 100 megawatts. But then this here represents deviation from a forecast of total demand. So if total demand was 1 gigawatt, and that was the forecast, and total demand ended up being 1.1 gigawatts, then I have 100 megawatts of deviation, and this W will represent the percentage of the deviation that this generator takes care about. So it's a very simple structured policy, but then we can build around that some algorithms and really find a solution for a multi-stage robust optimization problem. We don't know if that's the best solution. Of course, it's not the best solution. It's a simple policy again, but we ended up showing that in practice, it's not too far. Okay, so I just want to show you that even for a very large system, we ended up showing that this gamma represents how large your uncertainty set is, that this is 1% away from optimal. How do we know it's 1% from optimal, and no ideal optimal function? Is our lower bound here, we ended up comparing to an information relaxation of this problem. Okay, which is basically the relaxation is what is this piece, this P at time 1 knows all the D vector. P at time 2 knows all the D vector. And I forget of non-anticipativity. Okay, that's the idea. We used that and we were able to see that the policy is not too bad in practice. Yeah.
It's kind of surprised that the policy is a very simple form.
Yeah, super simple. Yeah.
It doesn't involve the bounds, the rim bounds, because we think that if the difference is too large, we violate the bounds.
Exactly. That's one of the constraining aspects. So for example, if this generator, I will need this. If there's a generator, what you end up having is, depending on your uncertainty set, a generator, you might know that it will move, I'm inventing numbers here, between 150 and 200. So your forecast is 175. This is the nominal generation of your generator. But depending on this sensitivity variable I showed you, that it could go up to 200 or 250. But then maybe in the next hour, this guy will move here, right? So 190 and maybe 180 and 200. I'm just inventing the numbers. So you need this to be feasible. So not all generators will be able to do that. And you end up seeing is this will immediately tell you what generate. This will employ the flexibility from those flexible generators. And some generators are able to do that from 1 hour to the next or something like that, and some are not, definitely not. So then you want to have this sensitivity, be reasonable with respect to what you can do on these ramp constraints which are here.
So when do you use the test? Because you have pre-specified format.
We actually build this in directly into the policy. We actually transform this constraint. If I write this very simple policy using these numbers, which is some WI plus something here, this just transforms into an explicit constraint. This part here, and then I just build that directly. And I don't need to, I just build it. I mean, the policy, one of the benefits of this policy is that you put this into that ramp constraint I showed you, immediately you can observe that you can immediately pre-compute those constraints and add some explicit constraints that tell this generator that, okay, if you want to choose this 200 and choose the 150, you have to be able to do this. Yeah. It will be embedded into the W, into the space for the two W's for your decisions. Exactly. Yeah. That was one of the benefits of this. Okay. So that's why I want to tell you about this part. Now I want to talk about a little bit more of convex optimization. Okay. So let's go back into that .com. Okay, so these are the bread and butter of electrical engineers over there. These are kicks of current. This is current balance. Okay, this is balance of current. This is Ohm's law. How current relates to some physical components at every node of the network to voltages. Okay, and then you have AC power. This includes the concept of active and reactive power, and these are really complex numbers that represent some sinusoidal signals in some perturbed space. Okay, in the phasor space. So this is balance of power in the network, and then based on that, you can write the power flow equation. So what I did is just replace all these numbers by some representation of these complex numbers. So here we have the real part and the imaginary part of those equations. Okay, so this is called active power and reactive power. This is injection from generators and demand from demand nodes. Okay. So based on this, so I don't want to go over details, but based on this, you can write the ACOPF problem. So this is alternating current optimal power flow problem. Okay, so I want to choose some active level from my generators, reactive level from my generators, voltage level at all nodes, and I want this to be satisfied. And this is angle level at all nodes. The angle represents the shift in your signal with respect to some reference. Okay, so this is a traditional thing. This has been written for maybe 100 years, or at least decades. Okay, but then some Diego's advisor here, and my advisor as well, and Burak was here a couple of weeks ago, right? Burak. Okay, so Burak is a genius. So they worked on this thing, and they basically said, okay, we can equivalently write this problem in this form. Okay, so just using the C and S variables, we represent these cosines and sines. And some trigonometric things we ask, and you can always recover from this problem these voltages. Okay, so these problems are equivalent. But then what they said is, okay, we can get rid of this constraint and relax this constraint here, and we obtain is an SOCP problem. Okay, second order column programming problem, and then this is a complex optimization problem that we can efficiently solve, and this can give us a very good bound for this original true problem, which is the true physics of the power system. So how do we, okay, then one other concept is some other people realized as well that you can also write this problem in this way. This is another equivalent way to write the ACOPF problem, but this is non-convex quadratic. Okay, so we have these quadratic terms, this xi times xj or ei times ej, fi, fj, etc. This is quadratic non-convex, but then we can do SDP relaxation for this problem. Okay, we can do SDP relaxation, and again, this is a convex problem. These people studied this problem extensively. Okay, so we have a suite of, ACOPF problem. We also have traditional linear models for this approximating this problem, and I'm not showing them to you. SOCP relaxation of ACOPF and SDP relaxation of ACOPF. Okay, so now let's jump into the real-time operation of the system. I'm operating the system in real time. Let's say this time is, let's say this is 10 minutes, 10 minutes, 10 minutes, so this might be 1 hour, okay, or something like that. So I want to choose all the time how I'm running the system, and then I have these round constraints we discussed before. So I want this solution to be reasonable for what comes in the future. Okay, but what comes in the future, when I make these decisions here, is really uncertain. I have uncertain active and reactive demand, and uncertain available renewable power from wind farms, solar farms, and so on. So what we worked on at the end of my PhD with Andy Sun is finding some solution here and writing some max min or worst case situation in these future time periods. Okay? And now if this is ACOPF, then I don't know that I can say anything about this max min problem. Okay? But if this is some reasonable approximation of ACOPF, maybe at least I can get some bad scenarios for the future of the problem. Okay? So what we did is we worked on this part using SOCP, SDP, and some linear approximations of the problem to see what would be a good approximation to try to find good solutions here under the true ACOPF equations, under the true nonlinear non-convex equations. And some of the conclusions here is SOCP is just the best balance. This SDP works, but it's too unstable. Using at the time the best SDP solver, which as far as I know was Mosek, it was too unstable. Whereas SOCP strikes the right balance in a way, okay, and gave us really good ways to see into bad outcomes in the future, and deliver us and help us find good solutions here, you know, and run the problem in a smart way. So we used a little bit of these ideas I showed you before, but we had to do some approximations. In particular, this max mean under some convex model, you can take the dual and you obtain here a biconic problem, okay, because this is a cone. And then we did some heuristics to solve this. Unfortunately, we couldn't do a lot more than that. Mm-hmm. There's not much guaranteed under some super simplistic circumstances, but in practice, in a lot of different cases, it reaches, I'll say something like 3 to 5%. Sometimes you get 0.1% far from optimal. In the worst case, I've seen up to 10%, but that's strange. Yeah, away from the optimal value. So in a lot of cases, these SOCPs and with some additional work into it, because I showed this arctangent constraint. For example, in that paper, they do some approximation of this function from outside. And they manage to reduce the gap and so on. So 10% is too much. I mean, it's usually 3%, 1%. It's really tight. Yeah. There's some super special circumstances, but you have to ignore a lot of the true aspects of the problem to find some guarantees. And also for the SDP, it's a similar thing. Yeah. Okay, so I just wanted to give you the idea there. Okay, something we're doing is using robust optimization to study how the power system should react to wildfires. Okay, so in 2017, we have the worst January recorded in terms of wildfires in Chile, and it did affect the power system. So what the system operators ended up doing is islanding the north part from the south part. Okay, close to Concepcion, they ended separating the Chilean power system into two parts. Okay, so imagine there's wildfire right here, starting here, and under one particular simulation, let's say it evolves over here in 24 hours. Okay, so this will be 24 hours of simulation from the blue to the red. So we have a very nice wildfire simulator. These are all pixels, and this can basically simulate fire going that way or going that way, and you really don't know where the fire is going. Okay, so based on some exponential random variables on and the fuel of the cell and so on, we have some reasonable wildfire simulator. And then on top of that, what we build is what we want to do is this: give me a good solution for the topology of the power system. You might want to turn off some transmission lines to avoid certain situations. It sounds paradoxical, like a paradox, why would I ever turn off transmission lines? But what ends up happening, this fire will affect some of your lines or some of your substations, your nodes, then you might want to actually turn off more lines, to build some reasonable topological structure, all aimed into maximizing the energy you supply to end users. Okay, so what we built is first of all, there's two things. You have this in 24 hours, but the other thing you have here is a lot of wind power. Chile doesn't have it right now, but they're building it. They're building that wind power gigawatts in the south of Chile, the Biobío region, coming into the next few years. So you will have this strange situation where you have trees and wind farms close by. So you have the joint uncertainty between wildfire evolution and wind power. Okay? So what we ended up building is this max-min problem where you give me some simulation and I'll tell you what happens with, give me a bad outcome for wind power and a bad outcome for what this simulation of the wildfire will destroy. Because you will say, of course it destroys the line. Not necessarily. It doesn't necessarily destroy the line. Those pixels burned, but that line could be okay. Okay? In some cases, it's not okay. It really affects the line. You have to turn off the line for security or something like this. Some cases it doesn't. It depends on the heat. It depends on a lot of things. It depends if you have a team that needs to cross by, you need to turn off the line. It's really complicated to see when fire affects some physical structure in the power system. Okay? So we try to look at that joint uncertainty and basically find bad scenarios for wind and for the contingencies that this wildfire will produce. And then based on some stochastic analysis and some Monte Carlo analysis for wildfire simulations, we can find a good topology for the system and say, let's turn off this and that line and prepare the system for bad situations. Okay? So that's work in progress. Okay, just some comments of energy planning. I know I talked a lot more about operations, but just 5 minutes about energy planning. Okay? So again, and back to our question, how will the system look in 2050? So a key idea when I want to think about the power system in 20 years from now, or even 5 years from now, okay? So is the idea of saying, okay, I want to build a power system that will be okay every day in 2030, in 10 years from now. So every day I need to understand the dynamics of January, the dynamics of February, March, But then what happens is I have a lot of water in some parts of the year, I have a lot of sun in some other parts of the year, I have a lot of demand in some parts of the year, I have more or less wind. So a key tool to understand how to plan for, say, year 2034 is to select representative days. Okay? So these are 6 different representative days, and this would be the generation profile in the whole system, Chilean power system. This would be coal, okay? This is hydro, run of river, hydro dam, then more hydro, gas in green. This white part is wind, and yellow is sun, okay, solar. So it's not a fried egg, even though it looks like one. Okay, and this will be like a strange fried egg. This is how my fried eggs look like when I cook. Okay. So this is 1 day, 2 days with a lot of wind, two or four days with a lot of solar. So it's really challenging. 6 is probably not enough to have a good understanding of a whole year. But with 6, you can still have different dynamics to plug into a decision-making model, an optimization model that will tell you how the power system should evolve up to that time. Okay? So I'm running out of time, so I just want to show you, I want to skip this part. So the kind of analysis you can do, okay? So desalation. I mean, in the north of Chile, there's a lot of mining companies that are desalating a lot of water. Okay, so taking salt out of water. There's about a gigawatt of demand only of power demand from desalation infrastructure. Now, this becomes a really interesting problem because what if I could control those desalating plants in a smart way to just use more power and desalate more when I have more solar power, say, or when I have more wind power. So what it ended up showing is, well, this shows a little bit of different dynamics under controllable and uncontrollable desalating machines in the north of Chile. And the main insight here was this one. In 2034, we expect that we'll have about 40% wind and solar power. Okay? Now, if on top of that, under the usual circumstances. But if in 2034 you are able to use these desalination plants from the north in a smart way, then you will jump from wind and solar power from 40 to 45%. That means 5% more variable renewable energy, cheap and sustainable variable renewable energy, only based on being able to control these desalinating plants. So again, this is also work in progress, and we're trying to see how to employ these energy planning models to see if there should be any more considerable efforts to control desalination plants. Okay? So just as an example. And then the other thing I want to show you is, again, back to this robust model. Okay? First stage, second stage. How we employ this structure in an energy planning problem, this is a published paper, is we do this. This X represents my investments on generation, transmission, and so on over the power network in the next 20 years. And this here will represent the operational dynamics under some bad day. So this uncertainty set here will give me a bad realization for demand, for wind power, and for solar power. Okay? So what we end up building is robust plans for how the power system should expand in the next 20 years. Okay? So this is again the idea. You have some uncertainty set and you find some bad load. So generation and transmission investments, okay, plus worst uncertainty realization and operational cost. This is this mean max mean structure. Okay, so again, the concept of clustering. These are 365 days of data clustered into three different clusters, okay, that we use to build these representative days. And now the point is building some uncertainty set over these different clusters. So we did clustering and we built uncertainty sets over demand, solar, and wind over the whole Chilean power system. And then I ended up seeing that this is basically this is cost over, this is average cost over a day in 2040, 20 years from now, okay? So average cost over a day, this is a traditional model, and this is the robust model we built. And this here represents your planning margin. This is some sort of reserve. So adding more generation that is super flexible. And this is some uncertainty budget in terms of that controls the size of the uncertainty set. So this is a very conservative plan, and this is a very unconservative plan. And based on simulation, you can find the right balance. Okay? And we end up showing is you can really control well here, using this robust model, control well the uncertainty in wind and solar power in this uncertain day of 2040. Okay? Okay, and just some ending comment. The other thing we're looking into is concentrated solar power. So this is a really nice technology because you can actually have solar power at night. Okay? So Seminario in Chile will be the first concentrated solar power plant of Latin America, of South America at least, that will be ready to operate next year. And it will look something like this. This is about 3 kilometers. Okay, I don't know if it's Seminario, but some plants have a diameter of about 3 kilometers. And you can actually have solar power at night. And not only that, you can actually control your signal, your injection of power into the system. So this is very sustainable because it's just renewable power. Not very cheap, it's very expensive actually, but very controllable. So it helps the power system quite a bit. So we did some studies and we observed that under reasonable trajectories for how the costs of this technology will evolve, then we expect that Chile will have about a third of its power, of its energy, of its electric energy, coming from this type of plants. Okay, which is crazy, but that's what the number says. The numbers of these models say under reasonable circumstances. Yeah. Yeah, exactly. So this is mirrors. Yeah, sorry about that. This is mirrors. This is not photovoltaic plants. This is not the photoelectric effect. This is just mirrors, okay? We don't need Einstein for this one. So just mirrors, pointing all the light up here, from more than 1 kilometer away, and then this will melt some sort of oils or salts, some type of mineral, something like that. It will melt at around 1,000 degrees, and then you can move it, and you have some valve or something to transform that heat into moving a turbine and creating power. But the thing is, you can choose when to open that valve and when to produce that power to a certain extent. So you talk about hours of storage here. So do I have 3 hours of storage, or I won't be able to go into the night? But if I have 12 hours of storage, I can easily use this plant to supply energy by night. So this will actually compensate what PV panels, what photovoltaic panels do, which will just immediately transform radiation into electricity. In the heat, in the melted salts. Yeah, exactly. Yeah. So this is a battery. This is exactly a PV plant with a battery. Not exactly, but from optimization perspective, pretty much. Yeah. Yeah. Yeah, so the typical thing is you will, I'm not an expert on the physical side, but yeah, you evaporate water, and that moves the turbine. Yes, you need water. Yeah, exactly. But I don't know, I think this water just stays in there. I don't think you need a constant stream of water or anything like that. So this is really nice. It's a lot more expensive than using the same space with photovoltaic panels. I don't remember the exact number, but this technology is evolving really quickly. So we will have 100 megawatts of this next year. The Chinese are building about 1 gigawatt of 8 different forms of this thing to try to see which one will scale. So maybe we'll have a revolution for this type of technology in the next few years. And then again, this is key for energy planning. So I'll stop here, and thanks so much for your attention. I'll leave it there in the beautiful image. Thanks, Diego, for the invitation. Yeah.
I have a question about battery storage. What's the expected evolution of technology?
What is the expected what?
Evolution of this year.
So as far as I know, the last 3 or 4 years have already been a revolution, because costs have dropped down like to 50% of it was 3 or 4 years ago. And I guess it's not only a matter of technology itself, but the logistics around this technology, just scale. And no one really knows if this thing will keep at that pace for how long, and if eventually you'll have some crazy revolution after different technology, maybe not lithium. Today it's lithium, the winning technology. But no one really knows. There's this company in Sweden, I think, that just promised to have built this new revolutionary battery. We'll see if that's true or not in the next few years. But it's a good question. Yeah. But we're already undergoing that revolution, I would say. Yeah.
I saw you had a couple of slides on the carbon tax.
Yes. So I'm not going to show the slide, but the effect is what you would expect, right? So right now you have so that's the thing. You can always just increase the cost of emissions, and that will drive your system in a different way. But as things have gone, I don't know, we do have a carbon tax right now, but the way it's been implemented is really strange, and it's not producing that effect. So then again, but what did work is this coal plants to eliminate coal, and in 2040, industry and the government have agreed that there will be no more coal on a day-to-day basis. They might keep them for safety or things like this, but we will have about 5 or 6, 8 plants being closed in the next 5 years as well. So it's a gradual transition to zero coal in 2040. Yeah. Is that enough? We don't know. Yeah, we don't know. Yeah. Yeah.
What are the multi-stage models by the stage?
So when I showed the multi-stage model, we actually found a multi-stage solution, which was the simple affine policy. But in the other model, the real-time model, we're actually ignoring the multi-stage, the true multi-stage dynamics of that problem. And we're building a two-stage approximation, re-optimizing and a simulation platform. Yeah, to see if that works and does the job in a way. In that case, we didn't study, so it's a good question. We showed that you can find some benefits, but then if you want to think of ACOPF, this non-convex model, and multi-stage, then I wouldn't really know what to do. Yeah, but so it's a great question. Yeah. Depending on how you build it, in the first multi-stage model, the two-stage was a relaxation of the multi-stage model. At least that version of a two-stage model, because you basically ignore the non-anticipativity constraints. Yeah. So we used it as a bound to see how good or bad was our affine policy. Yeah.
Questions? Okay, thanks again.
Okay, thanks so much. Thank you.